Hello dear students, Assalamu alaikum. My name is Engineer Mir Masood. I am lecturer Department of Technology, Sarhad University of Science and Information Technology, Peshawar. I am teaching you design of hydraulic structures, and today is your lecture number 6. In lecture number 6, we will study about seepage. So, what is seepage? Seepage is the slow escape of liquid or gas through porous material or small holes. So, when any liquid or gas passes through or seeps through or escapes through the pores of the material or small holes, so this is known as seepage. For example, you can see in the figure a small dam is created or constructed to store the water. So the storage water is seeps through or escaping through this material which is porous. So this seeping of water is known as seepage. Another diagram, we have a gravity dam which is constructed to store water. So the water is escaping beneath the structure, as the structure is constructed of strong material which is concrete and which is non-porous. So the water escapes beneath the structure through the material, through the bed material or small holes in the bed, and this escape of water or liquid is known as seepage. It may be through the structure or beneath the structure. Seepage is one of the applications of groundwater hydraulic. The aims of studying seepage in civil engineering are: number 1, to find the discharge of seepage through and beneath the structure. So the first aim to study the seepage topic is to find the discharge of seepage which may be through the structure or beneath the structure. As you can see the figures above, in the first picture it is through the structure, while in the second picture it is beneath the structure. Number 2, to find uplift pressure under the structure. The seepage water which moves beneath the structure applies uplift pressure. So we will find how much uplift pressure acts on the structure because of the seeping water. Number 3, to find solution for foundation and piping failure. These are the different failures which occur due to seepage, and we will find the solution for foundation failure due to piping. We will study about seepage theories. So hydraulic structure may either be founded on an impervious solid rock foundation or on a pervious foundation, means the hydraulic structure which we constructed that may be on an impervious solid rock or on a pervious foundation. Whenever such a structure is founded on a pervious foundation, means when the structure is constructed on such a foundation through which water can move, it is subjected to seepage of water beneath the structure in addition to all other forces. So the seeping water moves beneath the structure, and in addition the structure is subjected to failures which is caused by seepage, and also the structure is subjected to all other forces which acts on the structure, which may be the storage water forces, etc. In the figure you can see a dam is created or a structure is constructed to store water. This is the level of water, storing water This water applies pressure on the structure in this direction on the upstream side, while on the downstream side the water level is about this level, and this water applies pressure in this direction, and the uplift pressure due to seepage will, in case of tailwater, will be this much, and in case there is no tailwater exists, the uplift pressure on the due to seepage will be this much. This is the quantity of uplift pressure which will act on the structure from the downside. The water seeping below the body of the hydraulic structure endangers the stability of the structure and may cause its failure either by piping, also called undermining, or by direct uplift. When water seeps below the body of the hydraulic structure, it endangers the stability of the structure and it may cause failure of the structure either by piping, which is also called as undermining, or by direct uplift. First of all, we will study about failure by piping or undermining. So, when the seepage water retains sufficient residual forces at the emerging downstream end of the work, it may lift up the soil particles. This leads to increased porosity of the soil by progressive removal of soil from beneath the foundation. The structure may ultimately subside into the hollow so formed, resulting in the failure of the structure. So, in this type of failure, when we build or construct a structure of impervious material for storing water, the water on the upstream sides tends to move through the material or through the bed material beneath the structure by removing the soil with itself and moving towards the downstream side. As a result, the water which moves from the upstream side to the downstream side takes soil with itself and move it towards the downstream side. As a result, a hollow space is created beneath the structure, and as you can see, the water from the upstream side is moving towards the downstream side by removing the soil material or soil particles from beneath the structure. As a result, a hollow space is created, due to which the structure subsides and a structural failure occurs. When the material moves from the downstream from beneath the structures and hollow space is created, the storage water applies pressure on the structure and the structure subsides. So this is the failure by piping, which is also called as undermining. In the second, failure by direct uplift. The water seeping below the structure exerts an uplift pressure on the floor of the structure. In the second case, or in the second failure, the seeping water below the structure exerts uplift pressure on the floor of the structure. Means water is seeping. You can see in the diagram, water is seeping through here and it moves from upstream side to downstream side. While moving from upstream side to downstream side, it applies uplift pressure on the structure. If this pressure is not counterbalanced by the weight of the concrete of masonry floor, the structure will fail by rupture or by part of the floor. As a result, when this water seeps from upstream side to downstream side, it applies uplift pressure on the structure. If this uplift pressure is not counterbalanced by the weight of the concrete structure, so as a result the structure will fail by a rupture or by a part of the floor. Generally, there are three seepage theories, which are Bligh's theory, Lane's theory, and Khosla theory. These are the different seepage theories which we will study in this subject. Number first is Bligh's creep theory. According to Bligh's theory, the percolating water follows the outline of the base of the foundation of the hydraulic structure, means that the seeping water follows the outline of the structure, means it moves with the sides of the hydraulic structure. In other words, water creeps along the bottom contour of the structure. The length of the path thus traveled by water is called the length of the creep. And this seeping water, which is moving through the contour of the structure, here as you can see in the figure, this is called the creep length and it is denoted by L. So the path traversed by the seeping water, which is seeping through the contour along the contour of the structure, is known as creep length and it is denoted by L. Creep length L is equal to LH plus LV. LH is the horizontal creep while LV is the vertical creep. As you can see in the figure, this is the vertical creep while this is the horizontal creep. So when we add vertical creep and horizontal creep, this will give you the total creep. Further, it is assumed in the theory that the loss of head is proportional to the length of the creep. Also, the loss head or the loss of head on the upstream side is directly proportional to the length of creep. If HL is the total head loss between the upstream and the downstream and L is the length of creep, then loss of head per unit of creep length HL divided by L is called the hydraulic gradient line. So the difference between the loss in head on the upstream side and the loss of head on the downstream side is known as hydraulic gradient line. The difference between the two head losses is called hydraulic gradient line. So one hydraulic gradient line is here, some head loss is done here and some head loss is done here. So the difference between these two hydraulic lines, the difference between these two hydraulic heads or two head losses is called hydraulic gradient line, while the second hydraulic gradient line is here. Some head loss of water is done here while some head loss of water is done here. So the difference between the head loss between 2 points is known as hydraulic gradient line. Note, Bligh makes no distinction between horizontal and vertical creep. So Bligh assumes that the horizontal creep is equal to vertical creep, or they occur with the same speed or velocity, and there is no distinction between the horizontal and vertical creep, means they move with the same speed or with the same efficiency. Consider a section as shown in figure above. Let HL be the difference of water level between upstream and downstream, and let us assume that HL be the difference of water level between the upstream and downstream, and water will seeps along the bottom contour as shown by arrows. These arrows shows the seeping water which moves along the bottom contour of the structure. It starts percolating at A and ends at and emerges out at B. Water enters at A and seeps through along the bottom contour of the structure and it emerges out at B. The total length of the creep is given by L is equal to D1 plus D1. This is D1 plus this D1. As the water seeps along both sides of this pile, or you can say pile sheet, so one D1 is here and one D1 is here. So D1 plus this length is L1, again this D2 and L2, this is L2 and this D3 and D3. So these are the length of the creep, total length of the creep. So L is equal to L1 plus L2 plus 2 d1 plus d2 plus d3, which is equal to b, as L1 plus L2 is equal to b plus 2 d1 plus d2 plus d3. So this is the total creep length according to Bligh's creep theory. Now head loss per unit length of the hydraulic structure is equal to HL divided by B plus 2 into D1 plus D2 plus D3. So head loss per unit length is, which is hydraulic gradient, is equal to HL divided by L, means head loss divided by total creep length, and the head loss is HL divided by L into 2D1, HL divided by L into 2D2, HL divided by L into 2D3 will occur at location of the 3 vertical cutoffs. So these head losses HL into 2D1 will occur at this vertical cutoff. Here is the vertical cutoff, so the total head loss is equal to HL divided by L, means total creep length, head loss divided by total creep length multiplied by the length of the cutoff. So here D1 is 2 times, so D1 and D1, so it is 2D1. Similarly here it will be equal to HL divided by L into 2D2, and here it will be equal to HL divided by L into 2D3. So these are the 3 head losses which will occur at the 3 vertical cutoffs. These are the 3 vertical cutoffs. The hydraulic gradient line HG line can then be drawn as shown in figure. So the gradient line HG line can then be drawn as shown in figure above. So the hydraulic gradient line then drawn as shown in figure, it is equal to the head losses between the 2 points. So head loss 1 and head loss 2, between the head loss 1 and 2, the hydraulic gradient line is this one, while the second hydraulic gradient line is this one. Now, safety against piping or undermining. According to Bligh, the safety against piping can be ensured by providing sufficient creep length given by L is equal to CHL, where C is the Bligh's coefficient for the soil. Different values of C for different types of soils are tabulated below. According to Bligh theory, to ensure the safety against piping, sufficient creep length should be provided, and it is given by the formula L is equal to CHL, where C is the Bligh's coefficient, and for different soils different C value is given, which is shown in figure, or which is shown in table below. In table we have type soil, and for that type soil we have the value of C, and also we have safe hydraulic gradient, which should be less than that value. Number 1, for fine micaceous sand the value of C is 15, and the safe hydraulic gradient should be less than 1 over 15, as the hydraulic gradient, that is HL over L, is equal to 1 over C, as from this formula, if we divide HL by CHL by L and also divide both sides by C, we will get HL over L equal to 1 over C. So HL over L, which is the safe hydraulic gradient, will be equal to 1 over 15 or 1 over C. Number 2, coarse grained sand. For coarse grained sand the value of C is 12 and the safe hydraulic gradient is 1 over 12. Number 3, sand mixed with boulder and gravel, and for loam soil the value of C is 5 to 9 and the safe hydraulic gradient should be less than 1 over 5 to 1 over 9. Number 4, light sand and mud. The value of C for this light sand and mud is 8 and the safe hydraulic gradient should be less than 1 over 8. Note, the hydraulic gradient, that is HL over L, is then equal to 1 over C, and the 1 over C values are these values, Hence, it may be stated that the hydraulic gradient must be kept under a safe limit in order to ensure safety against piping, that is, HL over L should be less than or equal to 1 over C. Means the value of the hydraulic gradient line should be less than or equal to 1 over C. Second is the safety against uplift pressure. The ordinates of the hydraulic gradient line above the bottom of the floor represents the residual uplift pressure had at each point. Say, for example, if at any point the ordinates of hydraulic gradient line above the bottom of the floor is 1 meter, then 1 meter of water will act as an uplift at that point. If H dash meter is the ordinate, then water pressure equal to H dash meter will act at this point, and has to be counterbalanced by the weight of the floor of thickness, say T. So, the hydraulic gradient line above the bottom of the floor represents the total uplift, residual uplift water had at every point or at each point. If we have 1 meter of hydraulic gradient line, or the ordinate of hydraulic gradient line above the bottom of the floor is 1 meter, then 1 meter of water will act as an uplift at that point. If H dash meter is this ordinate, then H dash meter, then water pressure equal to H dash meter will act at this point, and it has to be counterbalanced by the weight of the floor, say thickness T. So uplift pressure is equal to gamma W into H dash. Gamma W is the unit weight of water, while H dash is the ordinate at that point, which is in meters. Downward pressure is equal to gamma W into G into T, where G is the specific gravity of the floor material. For equilibrium, let gamma W into H dash is equal to gamma W into GT. Since gamma W will cancel out with gamma W, we will get H dash is equal to G into T. Subtracting T on both sides, we get H dash minus T is equal to G into T minus T. Take T common, we will get H dash minus T equal to T into G minus 1. So T is equal to H dash minus T divided by G minus 1, which is equal to H divided by G minus 1, where H minus T is equal to H, ordinates of the hydraulic gradient above the top of the floor material, and G minus 1 is equal to submerged specific gravity of the floor material. So this formula will give you the thickness of the floor material. And this is the end of our today's lecture.